双子山武州レコス走り
So we're going to talk about Kubernetes for Pythonistas, and the root of this talk, I'm not going to try to dazzle you with all of the things that Kubernetes can do. I want to educate you a little bit on what containers are and why they're important to people, especially in Python. Many of these languages have very complex dependency systems, and it could be a barrier to entry, especially if you're building or distributing software. So we're going to go through this and think about this from the very beginning of how you would think about containers helping you, okay? Now, I heard this was a technical conference, so this is my last slide, if that's okay. Let me know. I can find lots of cat pictures on the internet. So we're going to be in this mode for a while, okay? So when I first started learning programming, I was about 24 years old, and I had that book. And I wrote my first Hello World program, kind of like this one. And Python is like magic. You write a few lines, and you really believe you're the real developer. I started applying for jobs immediately after this was done. Senior developer, Python, 5 minutes of experience. And you look at this code, and you're like, wow, this is pretty awesome. So I'm going to run it, and you always automatically know what this does. So we'll say Python, and then we'll say our app, py. Okay, this is sweet. And then you go to your browser. And this is where your life changes for the first time. If you're new, when you see this, this is when you run around your house, and your spouse is like, what are you doing? That is not impressive. Like, that's Hello World. I can do that on a piece of paper. But it's important, okay? Now, I got brave. My first Unix machine, FreeBSD. All right? FreeBSD people are serious. They have, like, tattoos of the mascot. Like, you know that's not ever coming off, right? So we got this Hello World thing going, so I was like, you know what I'm going to do? I'm going to run it on my server. It should be easy. I got this one file. This app py. So you copy it to the server. And it's tiny. And then you go to type Python. And nothing's there. And then you become a sysadmin. In FreeBSD, you do not install Python the easy way. You have to heat your whole house from the server. You compile from scratch. This is what you do. So after about 6 months, I got Python on my machine, and the app didn't run. And then I needed pip. 2 years later, my app was running. It wasn't that bad. But this is what we're asking people to do when we write code. We're asking them to go and figure out what version of Python they have, what version of the dependencies they have. God forbid if you're using some C extension. And trying to use that on a Chromebook is very funny seeing that in the airport. Like, your computer's going to run out of battery in about 30 seconds. So we have all these dependencies, and packaging has come a long way in Python, right? So we have this ability now to say, hey, here's what my app requires. I'm going to do pip install. And I just did a little tweet. I'm going to show you guys what it looked like. So I'm on my Mac. I'm writing this test app for the demo. And I do sudo pip install. You guys are already like, what the hell are you doing? So I'm like, yeah, I mean, what could go wrong? I have Python pre-built on my machine. They're like, dude, the first rule of Python is you don't use system Python. I'm like, hold my keyboard, enter. You type in your password, right? And it's like, your InfoSec team is like, what the hell are you doing? Nothing works anymore, but I have Flask and everything I need on my machine. So we're winning. Like, I had to do this. So we have our app now. And we started to ask ourselves that there has to be a better way of doing this. So when I used to contribute to Python, I told you we had disutils, and there used to be a war, setup tools, disutils. And then we made peace. And the whole goal was not to be... It's the state of the art in Python. And it turns out we literally reinvented the wheel. I thought this was a joke. I was like, no. It's not actually called wheels. They're like, no, man, this is what you do. And I was like, okay, wheels it is. So the truth is, packaging is a pain point for all languages. It's a pain point for all software. Things that work well are like your mobile device. You go to an app store, you bring the whole package down. And the reason why we can have a billion devices is because we do not ask users to go and install other software to use the software that they're interested in. It's simple as that. But we do the opposite when it comes to servers. We're making everyone's life difficult. Anyone ever heard of DevOps? Anyone know what DevOps is? I took a stab at it. DevOps is group therapy for sysadmins. And we needed it largely because of packaging. It's not just Python. All those packages need to be maintained. They need to be updated. You write a Python app and say, hey, install this, and all the sysadmins just sleep. So how do we make this better? And this is where I think containers become interesting. How many people think static linking is a good idea? How many people like containers? It's it's amazing to me that so few people think static linking is a good idea, but they like containers. This is static linking on steroids. It's a big tarball with everything. A full operating system is in there. You're linking everything. I saw one container that had like a Chrome browser in it. I'm like, what are you doing? So what we want to do is, how can we leverage these containers in a very smart way? So just so everyone's on the same page, a container, there's two parts to this. There's a packaging format. The goal is we package all our dependencies into a tarball. It is actually a tarball. And it's a tarball with a specific format, so we know how to download it, extract it, and be very efficient with layers. So what we're going to do is build one of these things. Now, I'm cash flow for this because these days, no matter what app you build, for some reason it downloads like 2/3 of the internet in order to work. But I'll show you what one of these looks like. So we have our application. So what we're going to do is start with this Docker file. So the Docker file here is, you'll see the first line there. It says from Ubuntu. Yes, that is an entire operating system to put our 2K application into. Now there's a reason for this. How many people here would say they honestly know all their software dependencies? Exactly. So when you don't know, you just bring in everything until it works. And then we get DevOps. So the next thing I do here is, there's a couple things happening though. We take all the tribal knowledge from wikis and runbooks, and we put them in a Docker file. Now this is not the best we can do, but it is a good stepping stone for the majority of the people building software. And we can do clever things like cache some of the layers. So even though that first layer is pretty big, it's actually only about 70 so megs, we can cache that on the servers, so we don't have to copy it once for our apps. Okay? So the next thing we're going to do here is going to do apt-get install Python 3. Everyone's using Python 3 by now. Please tell me it happened. All right, just clap in case you just pretend. And then we copy our requirements.txt into place. Now the goal of this whole thing is that now everyone has a very sane and clean build environment they can build their application. You can either give people the raw Docker file and they can build it themselves, or you can build it and store the artifact. Right? So if you've ever built any package of any kind, the goal here is to build an artifact and we'll store it somewhere. Now once we have the artifact, we can give someone the image name and they can run it. So we'll just build this here so we can see what we're talking about. Now, my Python is rusty. So if you see any bad code today, please give me a pass. Do not put it on Twitter. I promise to follow Pep8 later. Okay, so we have this entry point. So this is basically going to do the same thing I was doing on my command line. And we're just going to set that an entry point. All right? So we're going to make a This is a very fancy way of doing it. So we'll just do this Docker build command. So here what I'm doing is saying, hey, I want to build this image. And I want to run that command. But what I want to do is have all of the requirements be pulled down and run inside of a true root environment so that I have a clean build that's reproducible. So we'll run this now. Okay, so the lucky thing is here is that I'm having a bit of caching. So I didn't change any of the lines at the top. Now you can run into issues with some of this caching, but the nice thing is when you're building and writing applications, you want to iterate fast. You do not need to run the whole entire apt-get command or the pip command again. Those live as separate layers. So once you have that, we can just copy in our application and then we can run it. How many people think it's really easy to run multiple copies of an app on your machine? Not a lot of hands. How many people are using virtual env to solve this problem? Okay, so if you're familiar with virtual env to give us multiple Python environments, you can look at this runtime. So this is the other part of the equation. Once we have this tarball, we can run it under a runtime. So let's do this really quick. So we'll say docker run. All right, so what we're going to do here is we're just going to run our app to make it a little bit easier. So we're just running on 5,000 to 5,000. So we're just doing a bit of formatting so I can get to it. We're going to run this Hello World app. It's going to run in the background. So at this point, I should be able to hit it in my browser. And there it is. Now, I can run as many copies of this as I want, maybe map to different ports, but this only solves the laptop problem. We have this thing packaged. It's easy to distribute. It's easy to run as many copies as I want. But what happens if I have 5 or 20 servers that I need to push this to? How many people are familiar with scheduling? Every hand should be up. Every device that you have has probably more than one CPU core. And when you launch an application, there's a kernel that has to figure out where this thing runs. So you have a really effective scheduler there. What most people are doing these days in linear of a scheduler, we call it like the meat cloud. Okay? This is where you say, hey, run this application, and a human decides where it runs. And sometimes we track in a very fancy database, aka spreadsheet. And the problem with this is, if one of the machines dies, they have this thing called on-call. Okay? Machine goes down, you get a call, and you get to put the app back on the machine. So what we want to do is like solve this problem in a way that goes a little bit further than our laptop. So we have a tool called Kubernetes. There's other tools that do very similar things, but we're going to work with this for now. So I have about 5 nodes in my cluster. Now the goal with this is that I do not want to statically assign my apps to machines. They're designed to go away. I want to treat each machine as one collective or like a multi-CPU system and treat the whole cluster like a single machine. So we need a new API, we need some abstractions. So once I have this abstraction, we can package our container and we call it deployment. So let's look at this really quick. So we have this deployment object. So here is the container we built, and we have it hosted somewhere. So anyone that wants to run this app can pull this particular container image. Now some of you are like, well, how does the system know where to put this? Since a lot of people didn't raise their hands about what a scheduler is, I'm going to explain it. Now the fastest way I've done this without diving too deep into computer science and hijacking my whole talk, we play a game of Tetris. So, how many people here say they have fully automated deployments? Okay, now this is a worthy goal to get to. You click a button, and your app installs to specific machines. I'll show you what that looks like. You do that in Tetris. I'll show you. It looks like it's amazing, by the way, if you can get to this point. So, the goal is we want one-click deployments of all of our apps. Now, you need to know a whole bunch of information ahead of time in order for this to work. You need to know all error scenarios. You need to know if a machine is in maintenance or not. And you need to make sure there's no network issues because you need to be able to route around them, all in Bash. Python if you're lucky. So, what we're going to do is, this is one-click deploy. This is the DevOps holy grail I'm about to show you. Be ready. You ready? One-click deployment. Bam. One click. And then you leave. It's fully automated, by the way. But the problem here is your memory CPU is just on the floor, and you're losing. Now we're going to cloud provider. This is pretty good, actually. Spin up more VMs. So what does the scheduler do? So here's the difference. The scheduler has to actually examine every workload as it comes in. Now, this is the x86 architecture. You're not doing anything that fancy. But things are slightly different, so they have different shapes and sizes. The goal is we look at these workloads as they come in, and then we make a decision. So what Kubernetes does out of the box is what we call bin packing. So let's look at what that looks like. So here, we see a workload, and the goal is just to place it by examining it. Now we look at these workloads as they come in, and what we're doing now is just scheduling in a way that we try to utilize all of our resources. So this is memory and CPU. And look at all these workloads coming in. Now half of you are like, wow, this dude is really good at Tetris. If you can totally talk and play Tetris at the same time. Okay, but this is still bin packing that's happening here. Now you ask, ask, why is the scheduler doing this? Well, when we examine all the pieces here, what we want to do is make sure that we allocate things in a way that, imagine a machine learning job comes that needs that CPU, and you've been reserving that special machine because it costs a lot more to run things on it, and when the right workload shows up, you can place it there. And then when it's done, you get back all the CPU and memory. You got a Tetris on Twitter. So that's kind of the difference between just automation and this idea of orchestration. We want to have this online examination of every workload so we can actually use our machines effectively. And the goal here is that we want to be able to reuse CPU and memory the best way we can. So it's part of orchestration. So how do we do that for our own applications? So for our own apps, we have to make this deployment descriptor. Now, it's a big YAML file. It's declarative. But what you'll see here is that we have our app name. It's called Hello World. And then we're saying, Kubernetes, when you run this thing, I want you to go grab this particular image. And when you grab that image, I want you to extract it and run whatever the entry point was, Python, app py. And then I want you to also shape this workload. Now, the thing you got to think about, in order for us to schedule these things properly, we need to know the shape of the piece. This is why we have our memory and our CPU requests, so we know where it fits in a cluster. Okay? So once we have this, we can actually give it to Kubernetes. So kubectl, get pods. So what we'll do is we'll create this deployment object. Now, can anyone tell me what machine that it landed on? There's a break out like, number 4. But no, the schedulers have to figure out at runtime. The only thing we are asking is that we declare that we want one of these things running. So I said kubectl, get pods. We'll see that it's running somewhere. Now, the nice thing about this, let's look at what machine it's on. So it's on NF6P. And it has its own IP address, .90. But what happens if we were to destroy it? Alright, we're going to destroy the workload. Now, depending on where you work, you're either fired or you're going to get a call. So we delete the workload, and this is what we expect. We expect it to be replaced quickly, and it has a new IP. And the nice thing about a system like this is, when we replace the workload, we keep track of it. We know its IP address, so we can hook it up to the load balancer automatically. Now, if you've been doing this kind of work, this is just from decades of people doing these patterns, and now we've just baked into the infrastructure itself. It's kind of like the Python standard library. It's massive because there's no reason for people to rewrite these things over and over again. So these are things of pretty standard issue. If I look here, get SVC, we'll see that we have a load balancer that's routing traffic to all of those. So no matter what I do, I have a stable endpoint where I can hit my application, and there we go. It's up and running. Then it gets really complex. It's just like you can't run production Python by just using Flask. Anyone know why? One request at a time. My shooting game. One request at a time. So what do we do? So in the Python world, it's common to compare with maybe some Whiskey server or Nginx. So what does that look like in Kubernetes? I'll show you a log on the screen, so be prepared. So in the container world, one would say you build an even bigger Docker file, and you install Nginx in there, you put your Whiskey in there, and then you take a script to launch all of that in the background. Right? You just invented an init system. There's no reason to do that. What's a better approach? We don't want to pack Nginx into our apps container. We want those to be separate. So what does that want to be separate? So here's another deployment object. And this time, we'll do things in Selenium. I'm going to walk us through it really quick so you all can understand. This has multiple containers in them that we can stack. Think of it like a virtual machine. They're just going to run as processes that are co-located together to form the logical app. So we have Nginx. We're using Nginx shutdown. And then what we also are telling Nginx to do, you'll notice here in this particular line. Here, we're going to share this particular path. And what's going to be there is going to be our Whiskey Unix socket that is exported from our app, so we can actually send traffic to it in the way proposed by the particular docs. So here, we are sharing a file system. One container is going to create a socket there, and another container is going to pick it up and send traffic to it. But the nice thing about this is, everyone knows how your infrastructure is going to host. Nginx stands alone, and the app stands alone. So at this point, we can actually have Kubernetes manage this for us as well. kubectl, create, .f, deployments. Alright, so once this is online, get pods. Great. It's 202 ready, so we can actually compose these things. If you need any helpers, you can run your helper scripts as well. Now, once you have infrastructure like this, you start to think about, why do I need to use conventional ways of interacting with it? I've been using command line tools this whole time. So in the Python world, one thing that has been amazing over time in Python has been used as a facade for more complex systems like TensorFlow, most big data stacks. Python makes it super easy to interact with things. So if I were building new tools, how would I interact with this? Now, I think if more Python people showed up to the Kubernetes community, they would also look to simplify things. So I found a really good Python library. So I wrote a new interface to Python, and this is the first time I'm going to ship it to anybody. Okay? So if it doesn't work, remember, I wrote this yesterday. So bear with me, okay? So what we're going to do is clean up here a little bit. Get pods, kubectl, we're just going to delete these deployments. So it's really easy to spin these things up and down. Let's clear them out. And keep in mind the frame of reference I'm coming from. I've been watching Star Trek The Next Generation for some reason on Netflix, so I really believe I'm living in the future right now. So when I went to go build this thing, I wanted something that felt like that. Okay? So let's just do a watch on here. I'm going to show you my new tool. I'll show you. So, please don't, this doesn't work. Alright, so this should terminate. Let's clean things up. here is see if we could update this in place without dropping any of the packets here. Okay? Update the Hello World deployment.
What version of the application would you like to deploy?
2.0.
Updating the Hello World deployment to version 2.0.
Thank you.
Okay, I gotta admit, that was pretty dope.
And with that, I'd like to end the presentation. Thank you so much. Welcome to my talk, A Brief History of Time, by Riemann Heidegger. In the beginning, the dinosaurs roamed the earth. They died and became extinct because of their inadequate capabilities. In the void that they left behind, the mammals arose, and intelligent life came to this planet, and we invented Python dictionaries. Any questions? Would you like a few more details? All right, so my name is Raymond Heidegger. The theme of my talk is lots of smart people over time thought about the dictionary problem very, very deeply, came up with some ideas, presented their ideas, the world accepted them, and thought we had good dictionaries. Then someone else came along, thought about it very deeply, and had another innovation and another innovation. And I think what we have today is a confluence of about a dozen great ideas that span the course of about 50 years. And so I'd like to take you from the dinosaur era up to the present and then slightly into the future. There are those of you who know nothing about hash tables. You will know everything about hash tables shortly. There are those of you who learned about hash tables in school. Now you learn how they're done in real industrial strength production code. There are those of you who already knew that, but don't know what the latest innovations are in Python. We have propelled the future quite a bit forward in the last few years, and I'd like to take you on this journey too, where I think it's a somewhat magnificent, I call it an ending point, but evolution never ceases. Shall we begin? All right. So one little thing about me, what is my mission in life? It is to train thousands of Python programmers. I personally trained about 5,000 programmers. My company, Mutable Minds, Inc., I have a team of trainers, and we have trained about 13,000 people cumulatively. So if you have an interest in such things, call me, and let's begin. All right. Our journey. The beginning and the end. Let's do the overview first, which is... Where is... Do not reprogram your keys just prior to a presentation. There you go. So the importance of Python is built around dictionaries. Globals are dictionaries. Locals were at one time actually dictionaries. Modules have dictionaries. Classes have dictionaries. Instances have dictionaries. They're central to the language, which means that they're used everywhere and they're pretty darn important. One example is we have instances. So we have a class and we have several instance variables, and I've chosen Guido's. City is Austin, and his favorite fruit is apple. I just made all of that up. And we can loop over the instances and print them out. Common place everyday Python code. What I'd like to do is look what's behind it and look what it looks like. So behind each of these three instances is a instance dictionary. Where's the make big button? That's my favorite button. There we go. Okay, so we've got three dictionaries, Guido Blue, and then the next one Guido is Austin, and the next one Guido is Apple. And so that's a consequence of how Python is designed. Instances have dictionaries behind them. So what we'd like to do is see how these dictionaries are implemented over various versions of Python. Jumping right to the end to see where we ended up after all the evolution. In Python 2.7, each one of these dictionaries took 280 bytes each. And the ordering of the dictionary was Sarah would go first and Guido would go last. And that is deterministic. It is repeatable in Python 2.7. And the keys are scrambled. We actually say arbitrary because they're not re-scrambled every time. In Python 3.5, some things had changed. By 3.5, the size of the dictionary had gotten down to 196 bytes, which is very nice compaction. And this time, the keys are actually randomized so that every time you rerun it, you get a different key order. So they were no longer deterministic. Then Python 3.6 came out. It's the size a little bit smaller, 112 bytes, which is pretty darn amazing. And the key order is now deterministic, and it's the order that you added the keys, because after all, in the beginning, there was Guido, and from Guido came everything that you see around you. Okay, so Guido goes first, always the ruler of the kingdom in the order of dictionaries. In the Python 3.5 universe, he was just another schmo. Once in a while, he'd get to be a benevolent dictator. Once in a while, the rest of us would get to tell him what to do. In Python 2.7... list programmer knows the value of everything and the price of nothing. So a list programmer does store what we're called association lists, the key value pairs. So in this case, we have a list of tuples. Each one of them needs to be searched independently, but you can see there's a linear search for each of these, and we have multiple lists, and there's redundancy inside, wasting space like crazy, like list programmers are wont to do. Just saying. Remember, the dinosaurs, our parents and grandparents, were crazy people and didn't know all of the things that we know today. That was a trick. All right. So, what was the first innovation after the dinosaurs died off? It was called separate training. The idea is, instead of doing a linear search of a big list, how about do smaller linear searches of smaller lists? So the idea is take that one big list we had before and divide it into two. This is list number 1 and list number 2. Now if you search list number 1, you either get 1 probe to find Guido or 2 probes to find Tim. 1 for Sarah, 2 for Barry, and 3 for Rachel. This doubles the performance of the lookups. Last place. Pretty awesome. If 4 buckets would be good, what would be better? 8 buckets. Now, 8 buckets is kind of interesting. We actually still end up with a collision. Guido and Rachel are in the same bucket for these. By the way, I've got actual code behind this, so these are literally where the collisions are in using 9.27 hashing. But if I get the buckets big enough, eventually everybody will be in their own bucket, which means I will find them right away. The number of lookups is exactly 1. This is dramatically better than linear searching. So, does it sound like a really great idea? I think so too, but you'll notice little bits of wasted space in there. But in exchange for wasted space, you get very fast lookups. This is the advantage of sparsity. The problem is this dictionary gets bigger and bigger. Even with size 8, with 8 buckets and 2,000 entries. See if I can drive this computer. Here we go. With 8 buckets, I put 2,000 entries in it. The average chain would be about of length 250. And so as the dictionary gets slows down, or as it gets bigger, it slows down. In fact, there is a better way. The solution is to periodically resize the dictionary so that it's never more than 2/3 full. Essentially, we copy out all the key value pairs, then we loop back and set up a bigger number of buckets than we had before, and then we reinsert. So whenever 8 buckets is not enough, go and make 16 buckets. After 16 buckets, 32. And that, no matter how big the dictionary gets, it retains its performance. Pretty awesome? These people in the beginning were thinkers. And this is the way they teach it to you in school. But they teach a lot of important things out in school. Like here's an important thing that you typically don't find in the textbooks, which is that we cache the hash value. The idea is instead of this narrow table up above, we're going to add an additional column to it. And that is to actually store the full hash value inside. At first, this appears crazy. Why do you need a hash value when you're inside the hash table? Well, the problem is for a key, and you don't want to do it again. The solution to the problem is cache it, so we save it inside. At that point, the resize code becomes a little simpler. It says loop over our keys and values and the known hash value, and then reinsert it back into the new bucket in a larger, bigger table. So this is, by the way, this stuff is not pseudocode. It all runs, and I'll give you links to it. I'll combine it together into one big recipe and hand it to everybody so that you can play with all of these things. And the idea is, in textbooks, you don't see this. It isn't essential to the algorithm, and it makes it use up extra space. You see this third column here? Okay, so extra space. But it makes space is very, very... I'm astonished by this, even though I'm one of the maintainers of this code. When I timed it, I found that resizing a dictionary is about as fast as a list copy. It is essentially running at the speed of copy. It makes no calls to equality. It makes no calls to hash. It essentially just says, what is my current hash? Take it modulo some power of 2 and reinsert it into a new table and loops over the existing keys. It's incredibly fast, almost as fast as copying a list of keys. I think that's kind of cool, which is why we use this extra column. All right, so the next step up is faster matching. This is something that they don't teach in school as well. In school, they say loop over the keys until you find a match. If you don't find a match, raise a key error. The problem is, how do you know whether a key is matched? You do an equality test. Does the key equal the target key? That makes a lot of sense in textbooks because the thing that they're looking for is typically a number or something like that. So equality tests are very cheap. But in object-oriented languages, any object can define it under EQ. That's very expensive. For instance, comparing 2 decimal objects involves a lot of steps because we have to line up the number of decimal places first. There's not just a direct comparison values. And so a lot of work can be done there. Potentially, if you have a database record, you have to compare every one of the fields in order to determine that they're equality. The moral is, in an object-oriented programming language, you can't assume that equality is fast. It can be very, very, very slow. And if it's slow, do you want to do it all the time or do you want to avoid it? I would avoid it. And so there's 2 fast early outs. One of them is this notion that identity implies equality. If we have 2 pointers to the same object, 2 variable names pointing to identically the same object, we don't even have to look at the object to know that they're equal. Or equal to you. Doesn't that seem obvious to you? If there's 2 pointers to the same object, it's the same object? Sir, what's your name? Christian. Person on the front row on the far right side. What's your name? Ooh, I had 2 references to the same object. Did I have to ask it both time, or I knew the references were the same? Did I even have to ask to know it was the same guy? Identity implies equality. If that person sitting in that person sitting in that chair is the person who's sitting in that chair, regardless of how I refer to the chair. Does that seem logical and obvious to you? It does. Interesting. Everything in the Python world is a subject of contentious debate. In the world of floating point numbers, there's a concept of a NaN, not a number. The 754 specification of NANs defines NANs as not being equal to themselves. Are you equal to yourself? Or because you're not a NAN. But if you're a NAN, it would say no. And so the thought that dictionaries break NANs because if you use one as a key, I found the key and says I'm not really me. At which point, a person who is a diehard for NANs would say a NAN should not be you should be able to put it in a dictionary, but you should never be able to find it later. And then they hold up the specification IEEE 750 arithmetic. What what do I have that can trump an IEEE 754 specification? Something of greater than that, something we care about more. The ZennaPython. I hold up the ZennaPython Rock Timmy. I say practicality beats purity. If you put something in a dictionary, get it back out, that's very impractical. It's generally a bad thing. It makes it impossible to reason about the container. And if I make identity applies equality, I can make dictionaries very fast. Do you want dictionaries that are fast and practical, or do you want one that is, makes it so you can put hands in and show your mama cute brick? Okay, so I fight it with practicality beats purity. Periodically, though, once a year, somebody comes back up and posts, I put an N in a dictionary, and later I was able to find it. This is terrible! And I have to fight the battle once again. I'm afraid if I ever retire from Python core development, so we have what is known as a hash invariant. All hash tables require this. If two objects are equal to each other, then they have to have the same hash. They have to be in the same cluster so that we can go find an object equal to that object. Does that make sense? Now I'm going to get mathematical and logical on you like Dr. Sheldon Cooper from the Big Bang Theory. We will use modus tollens logic, and I will express the contrapositive of this statement. That's where you switch the if and the then and negate the then. It's called denying the antecedents. The contrapositive says if two objects have hashes that are unequal, if you were in two different clusters, then it means that you're not the same person. You're not equal to each other. So we flip it around to the contrapositive, and it gives us a fast match algorithm. Internally, dictionaries and sets use a fast match. First of all, they check for identity. Are the two objects sitting in the same chair? If the answer is yes, we assume that they're equal. Identity implies equality. This is extremely fast. It's just a pointer comparison. The next thing is we already know the hash of the object, and we already know the hash stored in the hash table. As a result of that, if the hashes aren't equal, we don't even have to test them for equality. We know that they are not equal to each other. And we have the slow test. If these two early outs don't, we finally have to do an equality test. Two fast early outs. If you knock these two lines out of Python, it cuts its speed by more than half. These lines kind of important. So you like identity implies equality, and you're not going to file a bug report about IEEE 750 coins. The world's not safe for NANDs! I see how it is. That is an interesting test. This one, though, I've known about for a very long time. The full impact of it, though, didn't hit me until we started to go to the 64-bit world. What are the odds that two hashes are going to be equal to each other and objects are not going to be equal to each other? The answer is 1 and 2 to the 64. That means that with this test in place, we never, well, almost never, like never in your lifetime or in the lifetime of the universe, we will never have a case where the key is equal to the target key. We never do an unnecessary equality check. So every dictionary and set lookup, if it finds a match, does exactly one equality test, even if there are collisions. Who thinks that's kind of cool? These odds are so great that I conducted an interesting and funky experiment. I replaced this line in Python with return true, which said if the hashes are equal, just assume the same object. Interestingly, the entire test suite passed. Django's test suite passed. NumPy's test suite passed. In other words, this is a very, very, very good assumption. How many of you think it would be safe if I just took out the equality test and said the two? You don't think it'd be safe? How many of you think it would be safe if I were to just take this slow equality test out entirely? Really? A lot of you think it would be unsafe. Now I've got another poll question. How many of you use Git? Git does exactly this. When it compares files, it doesn't look at the files. If the hashes are equal, it believes that they are the same. This was a really good idea until SHA-1 started to look kind of weak of late, so they're actively working on switching from SHA-1 to a different hash where a person can't produce a collision easily on purpose. All right, so all of this was great, but there's a problem. Separate chaining takes a deal of space by having all the pointers to many separate lists. So what's the solution? The solution is make the table more dense, get rid of all the pointers, and put all the buckets in one table. The downside of this is you introduce a risk of collisions, and the solution to it is using linear probing. So this is pure Python code for doing linear probing. It says look in position I and check to see if you found the key that you needed. If not, go switch to the next location and look there and look in the next place and the next place and the next place. So with here's what the table looks like. Interestingly, Tim was supposed to go in Sarah's slot, but because it was already occupied, he went to the next slot, wrapping it around. This greatly improves the density of the table. Pretty good idea? It is, except for one problem. Later, if we delete Sarah from the list, Tim becomes unfindable. By the way, is Tim Peters here? That's because Sarah got deleted. In fact, there is a better way. The problem is removing a key leaves a hole. The solution is to mark that with a dummy entry. And the dummy entry says this space was used by some key. When you're searching, go ahead and skip past this and keep on looking until you find Uncle Timmy. And here's the pure Python code for that. And you can see the idea is, wow, I'm going to speed up. Is it truly 15 minutes to questions? Okay, how many till people walk out the door? 20. All right, good enough. All right, so free slot is we track to see if we found any dummies. As we do the search, if we find a dummy, we remember where it is. Later, if we find a hole in the table, we'll go back, instead of using the hole, we'll use the original free slot, the dummy that we found, and that lets us reuse the slots. On the other hand, if we find a key, we can use that fast match that we just discussed with identity equality and the hash table check in order to do a quick check. And this is the core logic for dictionaries. This is known as Knuth algorithm D, and it was known right at the end of the 1960s. It appears in the Art of Computer Programming. Turns out our grandparents knew a thing or two after all. Multiple hashing. The problem with linear probing is that we end up with catastrophic linear pileup. The solution is every time you get a collision, do a rehash so that they don't pile up in the same place, so they split off in different directions. And so there's two tricks there. One is we use all the bits of a hash. We've got a 64-bit hash and perhaps a table with only 8 entries, so we only need 3 bits at a time. So we actually shift in 5 at a time, and that's called perturbing. In addition, there's a linear congruential random number generator that says take the current slot times 5, add 1, modulo the number of slots to find the next one. What's cool about this is it provably eventually visits every slot. It means that hash tables don't get caught in a loop when there's collisions. I believe Uncle Timmy came up with these ideas, and so this code is Uncle Timmy's code. Whenever you get a collision, we print out about perturb the bits, shifting in additional bits, multiply by 5, add 1, take a modulo, and update the perturb. So in this structure, we end up with no here's the collisions that came out for this as it's probing all of our route. I made this a fairly dense table, and I picked these names on purpose to create a lot of collisions. So that is an improvement on New's algorithm D. Are you trying to say that Uncle Timmy was able to come up with something that Donald Knuth didn't know? Pretty cool. Now, an early out for lookups is Victor Stinner here. So Victor Stinner is an awesome Python core developer who's been working very hard on improving the speed of Python. One of his ideas is that internally in Python we use dictionaries a lot, and we're often looking up method names, and it's the same method name over and over again, and we have to repeat the dictionary lookup every time because potentially the dictionary can mutate. The way is in Pet 509, which appeared in Python 3.6. He added a private version number to the dictionary, so every time we update the dictionary, we update the version number. That means that anything that wants to do avoid repeated lookups can just keep track of the version number. Say if the version number is the same, I don't need to do the lookup. Internals quite a bit. Are you trying to tell me that Victor Stinner came up with something that Uncle Timmy couldn't, who came up with something Donald Knuth couldn't come up with, which is better than the dinosaurs who use databases? The case. There's a problem, though, with that design. If you look at this table, there's holes in it, and the holes are quite wide. It is all 3 fields. And so there's an enormous amount of wasted space inside. This is my big idea. The idea was a compact dict. And essentially what I did was compress these down and got rid of all the holes. So all of the hash values, the keys, and the values are stored in a dense fashion, and there's a separate table of indexes that's very narrow. Interestingly, because we only have to have 8 possible slots, the indexes can be stored in 1 byte each. So this index table is only 8 bytes. It's actually smaller than the space it takes to store Guido's name, which I think is pretty awesome. It probably doesn't seem like that because Guido's got 5 characters, but string objects are bigger than that. They have some overhead. So the index table is essentially free in comparison to this. No wasted space. Dictionaries are compact. You got any idea of how they got smaller in later versions of Python? We got rid of all the wasted space. Are you telling me that I thought of an idea that Victor Stinner didn't think of, that Tim Peters didn't think of, that Knuth didn't think of, that the dinosaurs didn't think of, that the databases? That is in fact true. That said, there was a terrible problem. The problem is with my dictionaries, by the way, I'm getting history slightly out of order here to make it easier to explain. These things happen in a different order than I'm saying here. But the problem is we had a dictionary for colors, a dictionary for cities, and a dictionary for fruits. Notice that all of these have exactly the same hash values, exactly the same keys, over and over again, repeated. If you have 1,000 instances, you have 1,000 dictionaries where 2/3 of the space is completely redundant. This can't be solved by people like me or Victor. We're not smart enough. No, it came from a PhD, Mark Shannon, and PEP 412, and Keep Sharing Dictionary. The idea is we share the first 2 columns, so all of that compacts down to this, which means we've got 4 dictionaries in one little space here with no gaps in between. Do you see all these ideas stuck together really well? So let me take you into the present. Let me take you into the future. The future is something I'm working on right now with sets. Because this part is so cheap, it's only 8 byte. Would it cost me very much to make it bigger and to double the size of it and make it less sparse? The answer is no. I hear people clapping in the other room. That's a bad sign. Okay. And so the only difference here is not this data. It is this index table. It's twice as big as it was before. It's got 16 entries, which means it went from 8 bytes to 16 bytes, and it's still smaller than Guido's name. It's the size of 2 of these hash values. It's nothing in comparison to the total table, but I've doubled the sparsity. What's cool about this is one second. What's really nice about this structure is completely eliminated all of the collisions. If you make the table sparse enough, there's no collisions at all. And it turns out we can now make them sparse essentially for free. Who learned something new? So that's going to be in the future. Dictionaries will do even fewer steps to look up, and same as with sets. By the way, have you seen anything that looks like this before? Really? Yes, it was up at the top of the page. Do you remember what those dinosaurs did a long time ago? In the 3rd millennium, we reinvented databases with indexes. That said, they're pretty badass. They're compact, they iterate faster, and as a side effect of how we build them, they preserve order. So in Python 3.6, ticks are smaller and faster, space efficient, beautiful, and key sharing. And if you get 1 million instances with 1 million dictionaries, none of this data over here, these 2 columns, have repeated. In fact, the incremental space is just a space that is stored in values for that individual one. Who learned something new? All right. I had some odds and ends at the end. Let me just say a couple of them real quickly. We still need a SIP hash in Python. The purpose of that is, it turns out some people are diabolical and try and create keys that intentionally collide. We fought back against them by putting a cryptographic hash that's reseeded every time Python starts up, so it's very difficult to come up with keys that collide. Also, sets use a different strategy. They use chaining and linear probing, because sets are about something different than dictionaries. Dictionaries are about looking something up. Sets are about determining whether something is actually there or not. Dictionaries, you typically know the thing is there, you just don't know what the value is. Different use cases, a different balance of strategies. A popular thing to talk about on Hacker News now is cuckoo hashing, and a number of languages are using it. How well does that mesh with this? And the answer is nothing I've described conflicts with cuckoo hashing. Cuckoo hashing is simply a different arrangement of the index table, but the rest of this could survive. We could still do it. I don't think we should, because we have no need for densification at this point, given that we've already reached a maximum density. And cuckoo hashing is all about increasing the number of collisions, whereas making it sparse is all about decreasing it. And I think that would be a step in the wrong direction. Additionally, there's one other piece of logic inside. In a safe world, someone looks up a dictionary and they don't change it while they're looking over it. The analogy is, you put a ladder up on the side of a house, you take out a saw, and you cut out the ladder underneath you. That's what happens when you mutate a structure while you're iterating. And so we have logic to guard against that, so that the dictionaries and sets won't cycle. If you're interested, when I post all these slides, all of this combined together is in a single piece of code. This was something that I posted about 4 years ago. It is pure Python code. It is a complete implementation of compact dictionaries from scratch, and everything I showed you is